Hi again. Okay, so last time we ended with a question. We ended with the question of if you have finitely many columns, 2 columns, 3 columns, 4 columns, each of which goes up infinitely high, then can you count them? And we saw that the answer is yes. So the natural next question is what happens when you go from 2 columns, 3 columns, 4 columns to as many columns as there are natural numbers, column 0, column 1, column 2, column 3, column 4, dot, 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 dot. Okay, and the answer is you can count those too, although you have to be at least a little bit clever to do it. So there we go. We're looking for an array that's unbounded both in the up direction, like the previous arrays, but also unbounded in the across direction, so unbounded in columns and unbounded in rows. Okay, and we want to enumerate those. So once again, we take it back to the lesson that we learned starting with counting the integers. With the integers, you alternated between plus and minus. When we got to the cross product of two sets, we had to alternate between columns. If you failed to alternate with the integers, if you failed to alternate between plus and minus, if you just did plus, why, you'd never get to minus. With the columns, if you failed to alternate between columns, why, if you just went up the left-hand column or just went up the right-hand column, you'd never get to the other column. So too here, the problem that a person can have is you say to yourself, well, I'll alternate between the first 2 columns. No, that won't work because I'll never get to the third column. I'll alternate between the first 3 columns. No, this is clearly not going to get anywhere. Okay, so I know what I'll do. I'll start off in the first column, and then go to the second column, and then go back to the first, but then I'll go to the third column. That is to say, I'll do something like this. I'll do this first, and then second, and third, and now the mistake would be to go here. I'd never get over to the column that starts with 2's that way. Instead, I now go here, here, and here. And then here, 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 and here. Yes, 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 yes. So we're sort of sweeping up, sort of from the bottom left corner and across, doing what amounts to a breadth first search. Okay, so let's have a look. So I wrote all that stuff down. Here we go. We're looking at the thing associated with 0. The thing associated with 0 is going to be this guy right here. The thing associated with 1 is going to be this guy right here. The thing associated with 2 is this. And now, again, the tricky point here is that you can't then go only up the first 2 columns. You have to go out to the column that starts with 2's. So you then go here, 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 and here. And then go here, 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 and here, and etc., and off you go. Okay, so that's right. So that will enumerate every element in that doubly infinite array. Okay, I find these tables to be very handy when I'm trying to think through these problems. They're a big help. Okay, and this particular enumeration has come to be associated with the name Cantor, George Cantor. Okay, or Cantor's correspondence takes in the way we're going to do it is we're going to go from the pairs up to the singles. So it starts with the pairs of natural numbers and it ends with natural numbers, and so it's an unpairing function, or diagonal enumeration. It isn't really the diagonals; it's kind of the anti-diagonals. But sometimes words are not, that's just the way words work sometimes. I'm calling it Cantor of xy, and it is the one that's listed in the table. It so happens when you think about this, you can actually give a formula for it. The book talks about in the exercise where the formula comes from. The book talks about in the main body where the formula comes from. Perfectly sensible formula, but I'm not going to go through that in this overview. But you can give a perfectly reasonable formula for it. You take x plus y and x plus y plus 1, divide it by 2, and then add x. And for example, if you take, say, 1 plus 1, 1 plus 1 plus 1, divided by 2, and add 1, you get 4. Okay, so the inverse is the pairing function. So you can go either from bottom to top or from top to bottom. Here, if you go from bottom to top, that's Cantor's correspondence. From top to bottom, that's the pairing function. Okay? For our purposes, we'll often go in both directions, but we have occasion usually to go from the pairs in the other direction, from the pairs from bottom to top. So that's the one that I've named. So the lemma is, as so often happens in mathematics, we have some definition, and the lemma justifies the definition, that the definition makes sense. Otherwise, otherwise, if the lemma didn't work, you'd change the definition to make the lemma work. So Cantor's correspondence is a correspondence, otherwise it would be singularly ill-named. So Cantor's correspondence is a correspondence so that the cross product of n cross n is countable, and basically we just counted it. I mean, this table shows a person what to do here. This table here shows a person what to do, and the formula, of course, is lagniappe. It's an extra bonus, but it's a sort of baker's dozen, the formula down here. But nonetheless, this table shows you how to count. And furthermore, if I gave you not pairs but triples, or 4 tuples, etc., you get the idea. I mean, it's a little more intricate, but it's not that more intricate. So just as a for instance here, if you wanted to count, say 0, 1, 2, you could think of that as 0, 1, comma 2, and count it as 2 pairs. In any event, the cross product of finitely many countable sets is countable. We're most interested in the case of the cross product of 4 countable sets. That's the one that really we need. Okay, so the cross product of 4 countable sets is countable. And remember that countable means either the same cardinality as the natural numbers, or countably infinite, or finite. Finite is also fair. So it could be that in this cross product of finitely many countable sets, 4 countable sets, it may be that some of those are finite, because they will be. All right, you see why I'm interested in 4. I'm interested in counting 4 tuples, because that's what we're doing. We're doing 4 tuples. We're doing Turing machines. So Turing machines are sets of instructions. Each instruction is a 4 tuple. So by the above numbering result, we can number all the instructions. I could say to you, I'm thinking of instruction 4208, and you could take out a pencil and do the pairing function and the unpairing function and do a calculation there with x plus 1 and say, oh yes, I see it now. It's Q5, comma, you could figure it out. Okay, I'm going to, just for our purposes, I'm going to fix sigma as blank and 1. So that pairing is effective, meaning that you could do it with a computer program. In fact, the book goes through the derivation, but it's perfectly routine. And it takes in natural numbers and outputs the corresponding instruction, as well as a program that takes in the instruction and outputs the corresponding number. So it works in both directions. So we can effectively enumerate, effectively name with numbers the instructions for a Turing machine. Okay, so I can say I'm thinking about instruction 92, and you know right away which instruction I'm thinking about. So with that, I can number the Turing machines. I can say I'm thinking about Turing machine 408, and you can, with a little bit of calculation, know which Turing machine I mean. So here we go. Starting with Turing machine P, the prior paragraph converts each instruction into a number. So I get a set. I0, I1, I2, etc. I get a set. This is the set of 4 tuples, except that instead of 4 tuples, it has the number of the first 4 tuple, the number of the second 4 tuple, etc., all the way out to the number of the final 4 tuple. Okay, and now, how do you convert this to a single number? Because I want to count the Turing machines. I want to say that this is Turing machine 408. How do I convert it to a 408? Why, I just put it in binary. So write it as 2 to the I0 plus 2 to the I1 all the way out to 2 to the IN. That's a number. Okay, so I have converted a Turing machine, eventually a little bit of beep, beep, buzz, buzz there in the middle, but I converted a Turing machine to a single number. For every Turing machine, if you give me 2 different Turing machines, they will have 2 different numbers. For every Turing machine, there's a number, and that number is unique. Okay? All right, so that goes one way. That goes from the Turing machine to the number. Can you go the other way? Can you go? And it does it effectively. You can do it with a computer program. What about the other way? Can you go from a number to a Turing machine? All right, well, let's try to undo what we just did. Okay, you give me a number E. We'll be in the habit of naming Turing machines with the number E. So you give me the number E. I'll represent it in binary. Here we go. It's in binary. It's 2 to the j naught through 2 to the jk. And now I find instruction j naught. I find instruction j1, instruction j2, all the way up to instruction jk. Make those into a set. That's a set of 4 tuples. Now, we're not quite done, but we're sort of 95% of the way. We started with a number, and with a computer program, it has something to do with binary, with a computer program, I converted that number into a set of instructions. Now all that remains is, you remember the definition of Turing machine says more than a set of instructions. The definition of Turing machine has to check that the set of instructions is deterministic. That is, that no two of the instructions begin with the same QPTP. And obviously you can do that with a computer program. You could check all the instructions against each other. And if you find that the set you have, the set of instruction J0, comma, instruction J1, comma, dot, 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 instruction JK, if you find that that set doesn't meet your test, is not deterministic, why, okay, not a crisis, just output the empty machine. The empty machine it's a Turing machine, it's deterministic, it's just the dummy case. Okay, so what we have then is we have a way to go from Turing machines to numbers with a computer program, and we have a way to go from numbers to Turing machines with a computer program. Okay. So definition, a numbering, and we'll use numberings all the time because it's a way of describing what Turing machine you have. A numbering is a function that assigns to each Turing machine a natural number. You give me a Turing machine, it's got a natural. You give me this particular Turing machine, I'll say, well, that's Turing machine 408. For any Turing machine, the corresponding number is called its index number. I'll call it the index number. Or Gödel number. That's very common to call something Gödel number because Gödel is the historical source of this stuff. Or description number. For the machine with index E, we write PE. For the machine with index E, we write PE. When you look through the rest of the book, there's lots of PEs, thousands of PEs probably. The function computed by PE we'll call phi E. So if I say phi 408, I'm talking about the function computed, the input-output behavior exhibited by Turing machine 408. And is there a 408? Yeah, because if you give me a 408, I decompose it into binary. I then look at the instructions. Are they deterministic? Sort of stuff. A numbering is acceptable. A Turing machine numbering is acceptable. A numbering is acceptable if it's effective. So if there's a program that takes as input the set of instructions and gives as output the associated number, that's the first condition. And the second condition is that the set of numbers for which there is an associated machine is computable. And finally, there's an effective inverse. So you can go from the Turing machines, the instruction sets, to the number. You can go from the number to the Turing machines, and that inverse is effective. Okay, so you can write a computer program for one direction, you can write a computer program from the other direction. Okay, what we have in the prior slide is not quite the effective inverse because it doesn't back up when it finds non-deterministic cases, but it's very close. Okay, the book talks about that a little more. Okay, and now for the rest of the course, we're going to just fix some acceptable numbering, and I'm not going to worry about the details. The details are very important. A person can work through the details in great depth. That's fine. But at this point, we're thinking about other things, and we're just going to assume that there's a way to number Turing machines. We've fixed it, and we're going to use it for the rest of the course. And the exact details of which one we fixed and can you compute it quickly, we're just simply not going to worry about it. Okay. And you can only worry about so many things. We're not going to worry about that. Okay. That brings me to the observation that you can write down Turing machines, two Turing machines that do the same thing, but are different. Just as for example, you could renumber some of the instructions. You could put in dummy instructions that don't do anything. So for example, suppose you had a Turing machine that goes up to state Q4, And then the way this Turing machine halts is that it sends you to state Q5, and there's no state Q5, so the Turing machine halts. Now, add a state Q6, add a state Q7, add a state Q, have it do something. It doesn't matter what it does. It's never going to get there. Every computable function, if you give me phi sub 408, every computable function, in fact, has infinitely many indices, because you can take the computable function back to a Turing machine, and you can add dummy instructions to the Turing machine. That'll give you a new Turing machine with a new number, and you bring that forward, and you're now looking at phi sub new number. So if f is computable, then there are infinitely many distinct e's, where f is phi e naught, phi e1, et cetera, et cetera, et cetera. And in fact, we can effectively produce a list of such indices because I just told you how. If you give me phi sub 408, I figure out what Turing machine that is. I add to that Turing machine some dummy instructions, and then I produce the subscript from that Turing machine, because the numbering here allows you to go either from the subscript 408 over to the Turing machine, or from the Turing machine that you've padded to a new set of subscripts. Okay. I want to close here with an informal way to think about numbering, and the word informal, of course, is a red flag. It gives you a clue that this is not really the best way to think about it in detail, but it's a good way to think about it from a high level. I find that folks often have trouble with numbering. It just seems to be something very different from what they're used to. So try to make the connection here between numbering and what a person is used to. So here's a connection. So you write a computer program. Here's a computer program, perfectly nice. Oops, where's my pen? There it is. Perfectly nice computer program. Okay. You drop that. You save it in your editor. That drops it to the disk. This is my picture of a hard disk. It's not a very good picture. So that you drop this computer program to a hard disk. On the hard disk, or in RAM, I don't know. Anyway, on the hard disk, it's a set of bits. It's a bit string. It's a sequence of bits. It's a bit string. You can interpret that bit string as a number. So you can start with the computer program and interpret it as a number. If you give me the computer program, I can generate the number. That's just a question of looking things up in ASCII or Unicode or whatever encoding you're using. If you give me the number, I can give you the computer program. Almost. Talk about that in just a second. The idea is that there's an association between the computer program and the number. Association between the computer program and the number. And I can go with a mechanical device in either direction. If you give me the source code, then the mechanical device, my laptop, drops it to the hard drive. So clearly the mechanical device is doing that. If you give me the bit string, I can produce the mechanical device can produce the source code. And of course, that's exactly what it does when I double click on the file. Now, I caution, as with every analogy, it's a famous quote, George Box's famous quote about models. All models are wrong, but some models are useful. Every analogy is wrong, but some analogies are useful. This isn't perfect. So for example, if this string has leading zeros and you interpret it as a number, you'll lose the leading zero. Anyway, the point is that there's a natural way to think about associating programs, which we're thinking of as roughly Turing machines, and numbers, which we're thinking of as roughly bit strings. Okay, so this is something that you're used to thinking of at least a little bit. Okay, and again, the reference is effective. You go from the program to the bit string, or from the bit string to the program mechanically, uniformly mechanically. Okay, very good. Bye bye.